Here there's a picture of a couple of different integration strategies for co-packaged dies. On the left, we see an example where the two dies are both placed side by side on the common organic packaging substrate. And on the right, there is a silicon interposer introduced to interconnect the two dies side by side. With the organic packaging substrate, the discontinuities of the largest vias and solder balls in the link are eliminated because we're just staying on the top side of the package. The density of interconnect in this case is constrained only by the package design considerations, not those of the printed circuit board. On the right, we've got a silicon interposer, so the density can be improved even further because finer bump and routing pitches are achievable in the silicon interposer, due in part to the fact that it's the same material system as the silicon dies themselves, so they have the same coefficient of thermal expansion, and therefore they're mechanically more robust and stable. There is some additional cost, obviously, associated with introducing the silicon interposer on the right, so there's some trade-offs there. And it's important to recognize that die-to-die interconnect exhibits some properties that are different than interconnect on a printed circuit board. On-chip interconnects, we know, are heavily RC dominated because they're so narrow that there's a large series resistance associated with them, whereas printed circuit board interconnects can be designed to be relatively low loss transmission lines because there's nice copper with controlled impedances and relatively large dimensions possible. The interconnect on silicon interposers and organic substrates can lie somewhere in between these two extremes. They are very lossy per unit length, and with a characteristic impedance and propagation velocity that does vary with frequency. But fortunately, the links can be made very small, so some of these downsides can be obviated. This creates a unique signal integrity environment. So it gives rise to some fundamental questions. Should matching be strongly enforced when we're talking about a die-to-die link? And what are suitable low-power signaling and equalization approaches for such links? These are open questions in the area of die-to-die interfaces that are still being considered and debated. And you can see here we've tabulated some typical values for different styles of interconnect. We see that for on-chip interconnects, they start exhibiting transmission line behaviors at tens of gigahertz, whereas for printed circuit board traces, they don't become RC dominated until you get to the very, very low megahertz range. On the other hand, silicon interposers and organic substrates transition at frequencies in between these two in the range of tens to hundreds of megahertz. Let's look at the packaging and routing requirements for a very high density die-to-die interface. For example, let's assume we've got a relatively large die, 15 millimeters on an edge, and we want to realize a 15 terabit per second interface total going out this edge of the die. Now, if we assume a typical C4 bump pitch of 130 micrometers, that means this die edge is only 115 bumps wide. And if we use differential signaling, that's 2 bumps per lane, we've only got 57 differential lanes coming out that we can arrange side by side along this edge of the die, even if we use every single bump for differential signals. In order to get a total 15 terabit per second in and out that die edge, we're going to have to transmit and receive at 263 gigabits per second per lane, which isn't really practical. So the most common alternative is to then use multiple rows of transceivers here. So maybe we've got a transmitter and receiver up here, and then a second row and a third row. This makes the so-called escape routing quite difficult. That is, how do we route out the transceiver in the third row down here out through the die edge without interfering with the other rows of transceivers? Other alternatives that could be considered is to simply use a packaging technology with a finer bump pitch. That'll give us more total lanes and lower the per lane data rate required. Or use single-ended signaling. That'll again give us more lanes. Or another alternative that's being researched is to use simultaneous bidirectional. That is to use the same physical bumps for both transmit and receive simultaneously. Another limitation is, though, imposed by the wiring pitch that's possible on the packaging substrate, whether it's an organic substrate or silicon interposer. Our target here requires 1 terabit per second per millimeter of bus width. Now, if we assume that a 72 micrometer wiring pitch is possible in certain packaging technology, which is a typical number for an organic substrate. That means across 1 millimeter of die edge, we can side by side arrange 214 wires. That means our bandwidth has to be 70 gigabits per second per wire, or 140 gigabits per second per pair. Again, very, very challenging. It's more realistic to assume that we might achieve 35 gigabits per second per wire and make use of 2 layers of the packaging substrate. And again, that requires enough layers in the packaging substrate to accommodate that. So here's an example published over 5 years ago of silicon interposer-based co-packaged die-to-die interface. The transceivers are arranged side by side, flip chip bonded onto a custom designed silicon interposer, and then the whole thing is put on a board for testing. Again, the use of the silicon interposer enables a finer bump pitch and denser wiring than is possible with an organic package substrate. Here's a picture showing some test results. We see that in this packaging technology, a bump pitch of 100 micrometers was possible, and a dense wiring pitch of about 10 micrometers center to center is possible, again, because we're on a silicon substrate, not an organic substrate. You can see the test results here. Negligible crosstalk is observed because the signal integrity stays the same as we activate neighboring channels. 1 or 2 neighboring aggressors being activated, the signal integrity doesn't change at all at 18 or 20 gigabits per second. So this interface demonstrated 2 terabits per second per millimeter of die edge. The primary limit here was circuit speed, and preliminary analysis suggests that if faster transceiver circuits were designed, signal integrity could be maintained over an interconnect like this up to 30 gigabits per second per wire at wiring pitch down as low as 4 micrometers. So this suggests that with silicon interposer technology, very high die-to-die interface, very high bandwidth densities are achievable. Also, die-to-die interfaces can exhibit very good power efficiency. And again, the reason here is that the links are relatively benign with very little intersymbol interference, so very little equalization is required. Really, the only circuits required are serializer and deserializer, referred to here as a mux and demux, and some amplifiers, the transmitter and receiver. So the total power efficiency achieved here is just a fraction of a picojoule per bit at 20 gigabits per second per wire. Now, this doesn't include any of the power associated with clocking. It turns out in such die-to-die links, clocking power will often consume most of the power in the link, and is therefore its design is the key aspect of die-to-die interfaces.